Hello, and thank you for spending your time with us today. We'll cover two new selective, sensitive, and effective techniques for dealing with two of the most troubling problems we all face today in the environmental world: the analysis of microplastics in surface waters with TED GCMS, and measuring perfluorinated alkyl substances in outdoor and indoor air using thermal desorption GCMS. So we'll get right to it. First, we'll talk about the analysis of microplastics. So what are microplastics? Now, there's no exact definition. There is a reference document put together by ISO that references the approximate size. There are primary microplastics, which are microplastics that were built that way as small pieces of plastic. And there are secondary microplastics, which are created by degradation of larger pieces of plastic. These plastics can be thermoplastics, thermosets, but also elastomers. Water is usually in the matrix someplace, and there's a number of analytical methods that could be used. So let's talk about how what we're trying to find out. There is no catch-all analysis for microplastics. There's a number of things you want to know, like particle number and particle size, the morphology of the particles, the state of degradation or oxidation. But more importantly, we'd really like to get to the polymer IDs and the mass balances, because these are important. Mass balance and polymer ID can potentially identify the source of the microplastic. So this is an overview of the many different methods used to characterize microplastics. This is currently in an ISO draft method, CD 24187. We're going to focus at first on pyrolysis GCMS because it's really good at looking at mass balance. It's one way to get at that. So pyrolysis GCMS is close, but the samples are small in mass, between 100 micrograms and 10 milligrams, with about 1 milligram being pretty typical. They're small in size, less than a square millimeter. And if you're using filters to collect samples from water, several punches must be taken to the filter. Consequently, this results in needing to take many samples to get a representative result. So to deal with this shortcoming, thermal extraction desorption GCMS was developed as another way to get mass balance and get around the problems of getting a larger representative sample. So automated TED GCMS is the thermal extraction and pyrolysis of larger samples offline in TGA, followed by mass balance determination via evolved gas analysis in TD GCMS. So to give you an idea how this works, so you would take a water sample through a filter crucible, for example, and you would take a surface water sample. You collect the microplastics that get caught in this crucible filter. This is very nice because there's no punching or cutting of paper filters needed now, and this is suitable to go straight into the TGA. So once we have our filter sample either in a filter crucible, or we have perhaps maybe a soil sample we want to put into a ceramic crucible, it could be any kind of environmental sample, sediment, soil, filter paper, etc. And in TED, now our size is much larger. We can deal with samples as large as 100 milligrams effectively. We carry out pyrolysis of this sample inside the furnace of the TGA. This typically is between 300 and 600 degrees, more towards the 600 side. All this is done in an inert gas flow. This causes the polymer to decompose and fall apart into fragments that are identifiable. These fragments, when it decomposes, are collected as they pass by a GERSTEL twister. This is made of PDMS, polymethyl siloxane. Once these compounds have been collected by the twister, the MPS auto sampler picks this up and runs it automatically GCMS. So let's talk about that process briefly. Once inserted into the thermal desorber, thermal desorption occurs, followed by marker compound identification. So if you're looking at polypropylene, polyethylene, and polystyrene, for example, we're looking for marker compounds that tell us which one of these polymers we're originally dealing with. Software identifies those or rules them out, and then they're quantified consequently. So this is an example of some of the things we can do with TED. This is 8 different kinds of polymers: polyethylene, polypropylene, polystyrene, polyethylene terephthalate, and several others. What we're trying to do here, again, we're trying to look for marker compounds that are particular to the polymer. This allows us to identify the polymer, and we're also going to use several other compounds as ions. So this is an example of polyethylene as a way of doing this. We get great correlation between spiked mass of polyethylene and peak area, typical for polyethylene marker substances. So note that the use of 4 unique marker compounds make the data much more reliable. So we're looking at 4 different peaks here to identify polyethylene. All 4 must be present. All 4 are dienes, or 1N terminal dienes. So the only way these are going to be present is if polyethylene's there. Marker compounds are created during pyrolysis, and they don't exist naturally in the sample. That's making it very unlikely to have a false positive. So this is an example of looking at microplastics from street drainage. Here, styrene butadiene rubber was identified from tire wear. It ends up being around 4 to 10% by mass of the sample entirely. Notice that most of this is actually in the smallest size fraction. These samples were taken in several different filters to have different sizes. Most of this is out in the sludge, but there's significant amount of SBR in every part of the sample. So in terms of street drainage, SBR from tires is a significant contribution. This is another example. This is a polymer mixture done with pyrolysis GCMS in comparison to TED GCMS. This is the same size sample in each case, and you can see really quickly that on the pyrolysis graph, we get data, but we don't get enough of it. The TE gives us much more information. So if you want to learn more about this in much more detail, there's several journal articles out here. I'd recommend particularly the J-Chrome-A article by Dumchen, Eisentraut, Selena, and Braun. Very good paper. Actually, they're all very good papers, but more information can be found here. We'd like to thank, actually, the people who created the technique at BOM, Ulrike Braun, Eric Dumchen, Paul Eisentraut, and the remainder of the group, along with folks at GERSTEL, Ike Kleinebene, Juan Xiao Zhou, Jackie White-Cabbage, and Jack Stuff, and Laurel Varnelli for their development of this technique as well. If you have any questions, please contact us. And from now, we'd like to jump on to the topic, looking at the ways to look at perfluorinated alkyl substances in outdoor and indoor air using thermal extraction, GCMS. So what is PFAS, or perfluoroalkylated substances? There are several compound classes. Perfluoroalkyl carboxylic acids, or PFCAs. The most common one that gets the most press is PFOA, or perfluorooctanoic acid. There's also perfluoroalkane sulfonates, PFOS, PFOS. This is also the second most commonly discussed. Is not amenable to being done by GCMS, unfortunately. And then there's another compound referred to as Gen X. That's its trade name. It's a PFOA replacement. Rather than give you the long chemical name for it, that's the structure. And then there's telomeres. So these are usually breakdown components of these larger compounds. To make a telomer, take X regular carbons, for example, and finish with all perfluorinated. So as an example, the F82 for fluorotelomer alcohol is 8 fluorinated carbons, or fully fluorinated, plus 2 normal carbons, one of which has the OH sitting on at the end. So it's actually 10 carbons overall. So 8,2 is 8 fluorinated carbons, 2 regular carbons, and then the functionalities accrue at the end. Normal carbons are always next to the functional group, whether we're talking about an alcohol, an acrylate, or anything else. And then there's all kinds of bits and pieces. There's degradants of all of these telomeres and larger compounds. There's substitutions. To get around various patents and other things, companies would put a chlorine here or an iodine there. Consequently, because of all those substitutions, we get a lot of different variations. And currently, EPA is looking at over 6,000 known species, and that list is growing daily. So it's a pretty diverse set of compounds. It's not any one thing. It's looking at a large number of things. But definitely, there's a target class. There are several target classes we want to focus on, which we'll get to in a moment. Why do we want to use thermal desorption GCMS for indoor air as a way of looking at this? For air analysis, thermal desorption has a lot of advantages. Concentration. We can take 100 liters of air, and we can concentrate it down to a microliter gas injection into the GC. This gives us access to small, volatile, perfluorinated degradants that are hard to see by the LCMS methods used for this in drinking water. We get a wide coverage of VVOCs, very volatile compounds, to SVOCs, semi-volatile compounds. We also get neutral and ionic PFAS as well, like Gen X. And we can do low flow pumping this way, which allows us to do long sampling times, which results in large volume time-weighted sampling. There are some risks, however. For the lightest compounds, it's difficult or not possible because we can't really trap CS4 or C2F6. Large volumes of air, potentially large water load for the GCMS, because large volumes of air have significant humidity and significant amounts of water. So large volumes can also potentially overload the system, resulting in carryover or system cleanout if too much is brought on. And of course, as I mentioned earlier, we can't do sulfonates. So how does thermal desorption work? Well, in thermal desorption, we pick a tube that's appropriate for the analysis, in this case, a tube that works for PFAS. This is an example of what a tube might look like. This is a glass tube that has sorbents inside. That tube is connected to an air pump. So you can see in this picture, in this case, actually, we're going to hook up 3 tubes at the same time here into these cases, and we can take 3 samples simultaneously. The pump is started at a known time, air is pulled through the tube at a known calibrated flow rate, and at a desired time, the total sample, the pump is turned off, and thus we know the fixed volume of air that we've sampled. These pumps now have gotten very sophisticated. They record the start and stop time and the calculated volume all for you. It's very, very easy to do. So the tubes are then capped and carried off and brought to the laboratory. So what happens there? So in the laboratory, they're analyzed by 2-stage thermal desorption. In the first stage, we put a transport adapter on top of this tube, and an autosampler places that tube into a thermal desorber where it's leak checked, heat and flow are applied, and this can be done in a split or splitless mat fashion. This is an example of a tube that's has been loaded into a GERSTEL TD 3.5 plus thermal desorber. If you could see inside the TD, that's what you'd see inside, is the tube sitting on top of the focusing trap. So that's all done valveless. The focusing trap's necessary because we need to use a high flow to get things off that TD tube, but we need a relatively low flow for GCMS. So we blow things off the tube and recapture them on this focusing trap where they're gathered for later injection. That's done simply by reheating that trap, in this case very rapidly with flow, and the analytes pass directly on the head of the column. This also can be done either split or splitless. Now, one interesting thing about this, GERSTEL's been involved since the early 1990s in thermal desorption, and every system we've built has always been free of Teflon. So we never really had an interest in, we never had a need to use Teflon, but as it turns out, now with PFAS, that's very important because Teflon in the sample pathway can result in loss or gain of perfluorinated compounds. So let's talk about how to build a relatively easy PFAS method. Now, that's kind of killing with kindness. If you're an analytical chemist, you know that there is no easy method development. All these methods take a long time to build and validate. But we've done this at GERSTEL, and we have a very nicely done, validated PFAS method. So we choose a sorbent that we want to use for PFAS. I could go into that in detail. I don't have enough time today to go through that. But in short, that resulted in a custom set of sorbents that are we call now the GERSTEL PFAS tube. You need to use a column and a GC that's appropriate for PFAS. We got around to that. That was an interesting process. You'd think that these compounds who have molecular weights in the 500 range would be something you'd run on a DB1 or a DB5. No, it turns out that even because of all that fluorine, they end up being pretty volatile, and the 624 column is needed to do that. And then you need to look at the mass spec. So how are we going to do this? Are we going to stick with the normal SIM scan method on a single quad? We need to use a high-res instrument, a tandem MS-MS, a triple quad. And then once we get to that, you would build an MS method around that. Just for now, let's go ahead and just look at what this looks like on a single quad. What happens if you do this analysis in a relatively quote-unquote clean office environment? So we did that. This is where that slide came from previously. We took some samples in an office environment, steady temperature and relative humidity. We used those PFAS tubes I mentioned. We ran at 40 mils a minute for 24 hours. This ends up being almost 60 liters of air sampled. We did this in triplicate, so we'd have 3 replicates there. We also had an unspiked tube that was not run, that's set alone. All these tubes were spiked with PFAS before they were run. That was done on purpose because we needed to see, we have to assume that there's no PFAS in the room, assume there's no latent concentrations, but we spiked the tubes to simulate the exposure as if there were. And of course, you run an unspiked tube by comparison, that way we'll have some idea of knowing what really is in the room. And again, no Teflon in the sampling train, none in its sample pathway. All the little white pieces you see there in that picture, these little white pieces are actually polyethylene, high density polyethylene. They're not Teflon at all. So there's no Teflon in the sample train. So this is an example of one of the spike standards. This is the fluorotelomere acrylate. This is the most behaved out of all of these, and we'll call it the good. Nice high mass results in a pretty much flawless background, nothing else nearby. At 518 AMU, there's not too much floating around that you'd pick up except the actual analyte we're looking for. Unfortunately, this is the only one. 518 ends up being the molecular ion for this, and it's the only one that had a strong molecular ion. All the other ones fell apart. But high mass equals low noise, low risk of interference, low risk of false positives. The low noise, of course, is going to mean great detection limits. Unfortunately, that was, again, the only one that behaved well. Looking at the MIFOSA, which is one of several compounds we looked at, I think we looked at a total of about 14 different compound classes. In this case, the most dominant ion for MIFOSA ends up being 94. So this is SIM done on 94. We did 3 other fragments for verification, but the point being here, you can see that as the mass gets lower, we end up with a lot more noise. That noise is bad because it's going to end up resulting in higher risk of false positives and also higher detection limits because of all the noise that's there. So you've seen the good and the bad. Now let's talk about the ugly. The fluorotelomere alcohol 8,2-FTOH. This is SIM at mass 31. Now, if you're an experienced mass spectrometrist, you're asking, why would you do mass 31? In this case, it's because you have very little choice. It's the strongest ion that this FTOH produces. You want to try to use it for quantitation. But you have to ask, especially here, now you see the spiked versus unspiked tube, is it real or is it matrix? So you don't know, you have a high risk of false positives now at this low mass, and this is a consequence, and this is a real problem for fluorotelomere alcohol. This, particularly for this compound, which is it's very much of interest to EPA and others for groundwater contamination and vapor intrusion into basements and other things. So this is going to be a challenge. So low mass equals high noise and high risk of false positives. So the limitations of there's some limitations of using a single quad in SIM mode for PFAS in indoor air. The MZ31 fragment's not ideal. It's the most abundant though. There are other ions, but they're even smaller in abundance. Although better than 31 MZ, the other ions are also low in mass. And of course, any of these alcohols will never give you a molecular ion to begin with in an electron impact based ion source. If you take all of that and you add to a near continuum low mass background that comes from this huge amount of air that's sampled, and you have a recipe for matrix interference and false positives. So, and pretty much with the exception of FTAC, which you saw previously, all of these compounds fall into this predominantly low mass ion trap. So we end up having this issue. There is a way to deal with it. This is kind of a spoiler alert. This is the same 400 nanogram spike of FTOH, or in this case PFOA, but now done on MS-MS with a triple quad. So note now, this is FTOH. Note now we're using an MRM transition of 131 to 69, and we virtually eliminated the noise and background. So we end up building a method. We found a sorbent that worked, we found a column that worked, and in the end, SIM scan's okay, but tandem MS-MS is far better for large volume air sampling for indoor air or outdoor air if you're also doing large volume air sampling due to the high matrix at such a large volume sampled. So the use of MS-MS will greatly reduce the background for all of these analytes. Spoiler alert, actually down in the single digit part per quadrillion in some cases. So really grateful in the PFAS work for the help of Dr. Jack Stuff and Jackie Whitecabbage at GERSTEL, who did all this work. I'm just fortunate enough to be able to talk about it today. The work was inspired by Heidi Hayes at Eurofins, who helped figure out a lot of the issues behind sorbent selection and also what classes of compounds we should be looking at. Jesse Miller at CAMSCO helped us get a hold of those tubes, helped create those tubes that are specific to this analysis. Also want to thank Tarun Animal and Tim Congelco at Agilent for their encouragement and particularly for the support using the triple quad for this work. And several colleagues at US EPA who were also behind this and gave some ideas and support and encouragement for getting this done, especially for what to look for, where, and why. That's still an ongoing question. 6,000 compounds and growing, and we're still trying to understand where they all are. So, and of course, thanks to all of you. Thanks for listening today. Hope this was great and hope you had a chance to learn today. If you have any questions, please reach out. My email address is here along with my LinkedIn address. Please feel free to reach out to me at either place. Keep an eye on us at LinkedIn and on GERSTEL US for new developments in the PFAS method and also in microplastics. And of course, there's a lot of great content on what we're doing on YouTube, both in terms of the science and what we're doing, but also basic things like how the instrument works and how to maintain it, etc. Thanks again. I appreciate all your time, and I hope you have a wonderful day.